Look at a modern suspension bridge or a massive hydroelectric dam. These structures project an aura of absolute permanence. Millions of tons of concrete and steel, engineered to stand immovable for centuries. But they are under constant, violent assault. Every heavy cargo truck passing overhead, every extreme swing in summer heat, and the relentless creep of time exacts a severe physical toll on these materials. For decades, the primary way to ensure these titans remain standing was periodic manual visual inspections. Crews of human engineers would scale the cables and walk the concrete decks, relying entirely on their own eyes to spot signs of physical decay. Relying on a visual sweep creates a massive operational blind spot. If a structural flaw develops deep inside a solid concrete pillar, human inspectors will never see it, until the exact moment the damage becomes critical enough to bring the whole structure down. Deep inside the main support pillar of a heavily trafficked bridge, the tremendous physical stress finally breaks the material. A jagged, microscopic fracture tears through the center of the concrete. Under the traditional inspection system, that tiny fracture sits in the dark for years, slowly inching outward with every passing car, remaining entirely unseen. To solve this, engineers deploy structural health monitoring, or SHM. SHM is the process of continuously tracking a structure's condition using digital sensors and automated data analysis. Instead of a passive block of dead concrete, the pillar is wired with an internal digital nervous system. The bridge itself becomes an active, communicative network capable of reporting on its own structural integrity. Catching that microscopic tear the exact millisecond it fortens separates a cheap, routine weekend repair from a massive, fatal collapse. The instant that microscopic crack snaps open inside the pillar, the bridge's sensor network reacts. This diagram illustrates our first defense: acoustic sensors. When concrete separates, it emits a high-frequency snap that these sensors intercept. Instantly, the pillar alters how it handles traffic weight. The physical load detours, concentrating massive strain on the surrounding concrete. To measure this exact physical deformation, the system relies on strain sensors and fiber optic sensors. Fiber optics are highly durable glass threads that measure incredibly tiny physical distortions by tracking how light travels through them. Because the pillar is carrying weight differently, the bridge sways differently in the wind. Accelerometers, instruments installed to measure changes in velocity and vibration, capture this abnormal rhythm. Simultaneously, GPS sensors are checked. These global positioning tools monitor large-scale displacement to verify the massive structure hasn't simply shifted from its foundational anchors, and temperature sensors log the ambient heat. Concrete naturally swells in the summer sun, so monitoring thermal effects proves that this sudden structural shift is actual damage, rather than normal physical expansion from a hot afternoon. Any single reading might be a false alarm, but when acoustic, strain, vibration, and temperature readings all spike in one localized area, the overlapping array definitively proves a fatal flaw exists, all without a human eye ever seeing the concrete. The physical crack happens in a fraction of a second. The challenge now is managing the invisible flow of digital data generated by those sensors. All of those precise measurements flow into the data acquisition system. This acts as the critical central hub, gathering the raw measurements from every single node wired across the bridge. This diagram represents the severe problem of data complexity. The system has to filter out the massive, chaotic noise generated by thousands of daily commuters in order to isolate the single, bright red warning signal of that microscopic crack. This filtering happens while battling the physical environment. High decibel traffic noise heavily interferes with acoustic readings, and harsh weather constantly degrades the physical durability of the sensors themselves. Once the true signal is isolated, it enters the data transmission phase. The warning successfully escapes the harsh environment of the bridge and is beamed out to remote servers. A multi-million-dollar SHM system is only as valuable as its ability to protect and transmit a clean, actionable warning signal through the chaos of the real world. Miles away from the wind and heavy traffic, the transmission arrives at a quiet, secure processing facility. Here, in the data processing phase, complex algorithms rapidly translate those raw electrical and optical signals into clear, readable structural metrics. This initiates the decision-making phase. This dashboard displays exactly what the human operators see: a targeted, localized alert. The process data points precisely points to the exact sector of the lower support pillar where the concrete is failing. Because the engineers know exactly where to look, they dispatch a specialized maintenance crew. Directly to the hidden flaw, the crew drills into the specific section and injects a high-strength epoxy into the expanding void. The microscopic crack is locked entirely in place. It is sealed permanently and cheaply, long before it has the chance to spread into a wider structural deficit. A few hours of targeted labor and a specialized industrial epoxy prevented a catastrophic structural failure that would have commanded hundreds of millions of dollars and an incalculable human cost. When you scale that highly targeted, preventative approach outward, the implications for society are immense. Structural health monitoring is rapidly expanding well beyond suspension bridges. Engineers are integrating these networks deep into massive hydroelectric dams, along miles of underground transit tunnels, and the foundations of offshore structures. The primary purpose of this massive expansion is absolute public safety. By eliminating visual blind spots, operators ensure fatal structural failures are caught completely before they happen. The secondary benefits radically improve infrastructure management. By shifting away from reactive emergency repairs and toward proactive, smart management, municipalities sharply reduce their long-term maintenance costs. A moment of wonder. Embedding digital sensors directly into concrete and steel produces self-diagnosing systems that actively alert us to decay, protecting the civilizations built upon them.